Hey everyone, and welcome to this explainer. Okay, if you're tackling this material for the first time, you are in exactly the right place. Today, we're moving way beyond the basic idea of just typing code into an editor. We're going to look at the massive, real-world, logistical, and structural problems that professional software engineers face every single day.
Okay, let's dive into this. Here's our roadmap for today. We'll start with an introduction to implementation, move on to the 4 levels of reuse, then tackle configuration management, look at host target development, and finally wrap up with a final exam summary.
Part 1. Introduction to Implementation, Moving Beyond the Code.
A lot of standard programming textbooks focus entirely on the logic of writing a program, but they kind of ignore the messy, complex, logistical issues of professional implementation. There's this naive assumption that software development is just amateur programming, writing code entirely from scratch in complete isolation. But professional implementation, it's a whole different ballgame. It requires managing the reuse of existing software, keeping track of countless versions of code, and dealing with entirely different hardware platforms. So today, we're going to break down the 3 major solutions to these professional challenges.
All right, Part 2, the 4 levels of software reuse.
Let's kick off our first major topic, software reuse. Look, if there is one single thing you take away from this section, let it be this: writing software entirely from scratch is basically obsolete. Modern software engineering is all about assembling existing parts. We define software reuse as an approach to development that's based on reusing existing software components, frameworks, or even entire systems. Now, from the 1960s through the 1990s, we wrote pretty much everything from scratch. But today, because of intense schedule pressures and sky-high development costs, reuse is the absolute norm for web-based systems, scientific software, and embedded systems.
So there are 4 distinct levels of software reuse that you absolutely need to know. First up is the abstraction level. Here, you aren't reusing actual code, you're reusing successful knowledge, like architectural and design patterns. Second is the object level, where you directly reuse standard libraries. A classic example here is using the Java Mail library to process emails in your code. Why write that from scratch, right? Third is the component level. Components are essentially collections of objects working together. Think of reusing a user interface framework, where you just define the screen layout and the colors. And finally, the 4th is the system level.
Let's actually expand on that 4th level, system level reuse, for a second. At this level, you really aren't writing code to build an application at all. You're reusing entire commercial off-the-shelf or COTS applications. The engineering work here is completely different. It mostly involves configuring these massive systems to do exactly what your organization needs, or maybe integrating several generic application systems together to create something brand new.
Now, here's a very common misconception. Students often assume that because we're reusing existing software, it's completely free and instant. But there are hidden costs. It's not a free ride. You have to spend valuable time just finding and evaluating the right software. Then, there are often high purchasing costs for those off-the-shelf systems. You also have to pay for the time to adapt and configure them. And honestly, perhaps the trickiest bit of the whole shebang is the integration complexity. This gets especially messy when you try to integrate reusable software from different providers who have made completely conflicting assumptions about how their software should work.
So, let's do a quick recap of this topic to lock it in before we move on. Writing from scratch. Super rare. As a professional, you're going to reuse software at the abstraction, object, component, and system levels. But you must always carefully weigh the time and financial costs of integrating those reused parts.
Moving on to Part 3, Configuration Management Essentials. Now that we've covered how we assemble the parts, let's look at how we actually manage them. I want you to imagine an absolute nightmare scenario. You're working on a massive project with a team. What happens when 2 developers open and edit the exact same file at the exact same time? Well, if there's no system in place, one programmer will save their changes, and the other will save theirs right after, completely overriding and destroying their teammates' work. Literally hours of work just gone.
So, the crucial point is that we desperately need a way to stop this kind of code destruction. And the industry solution for that is called configuration management, or CM. We define CM as the general process of managing a changing software system. Its core purpose is to support team integration, track component versions, and make sure everybody can access the most up-to-date code in a highly controlled, safe way.
And this brilliantly illustrates how that process flows. Change proposals come in right at the top. Those are handled by change management, which feeds directly into managing system versions, and that ultimately leads to system building and finally system releases. To achieve this seamless flow, there are 4 fundamental activities we rely on.
Let's break down those 4 activities. First up, version management. This keeps track of different versions and stops those nasty overwrites we talked about. Industry standard tools for this include things like Git or Subversion. Second is system integration, which helps define which versions of components are used to automatically compile and link the whole system together. Third is problem tracking, using tools like Bugzilla to keep a close eye on bugs and, more importantly, exactly who is fixing them. And fourth is release management, which is all about planning and organizing how those updates are packaged and pushed out to the customer.
Okay, time for another quick, easy-to-follow recap. Configuration management is basically the shield that prevents developers from accidentally overwriting each other's work. It achieves this by managing versions, automatically integrating systems, tracking bugs, and organizing releases safely.
Part 4. Host Target Development Platforms. This brings us to the third major implementation issue. We're now signaling a shift away from team logistics, and we're looking directly at the hardware environments themselves. We need to explicitly define 2 completely different environments here. First is the host platform. This is simply the developer's laptop or PC where the code is actually written. Second is the target platform, and this is the actual hardware where the software will eventually run. Now, sometimes they're the same thing, but for embedded systems, they are radically different. Just imagine writing code for a microwave oven. Your laptop is the host, but that microwave, that is the target.
Let's see how this works step by step. On the host side, the development platform is filled with all your tools. You write your code there, and then you have to download that software across to the target execution platform just to test it. Now, constantly downloading uncompiled code to a physical piece of hardware, like a microwave or a smartphone, just to run a quick test, that is incredibly tedious. So, we often use simulators on the host machine to mimic the target hardware. Simulators speed up development incredibly, even though they can be expensive to develop and are usually only available for popular hardware architectures.
To manage all of this complexity on the host machine, professional developers use an integrated development environment, or an IDE. An IDE is essentially a framework that hosts a massive set of software tools. We're talking compilers, debugging systems, and graphical editors, all within one common user interface. Eclipse is a fantastic textbook example of a general-purpose IDE that you can tailor with specific plugins for exactly what you need.
All right, recapping this topic. We always write our code on a host development platform, usually relying on an IDE like Eclipse. We then execute that code on a target platform, often relying heavily on simulators to bridge that hardware gap and speed up our testing cycle.
And finally, Part 5, Final Exam Summary. We have covered a lot of ground today, and I really want to explicitly point out that understanding these real-world logistics is exactly what separates a simple student programmer from a true professional software engineer. Here are the key testable facts that are highly likely to pop up on your exams. First, you must be able to list the 4 levels of software reuse: abstraction, object, component, and system. Second, you absolutely must be able to define the core purpose of configuration management. Remember, it's the process of managing change, tracking component versions, and crucially, preventing team members from accidentally overriding each other's code.
I want to leave you with a provocative thought as we wrap up this explainer. Today, we learned how to implement a system by mastering code reuse, version control, and complex hardware environments. But think about this. What happens once that system is actually released to the public? How do these exact same tools scale up to manage software evolution and maintenance over decades? Because that is a whole different beast. And that is exactly the question we'll tackle in our next lesson. Keep learning, and I will see you then.